So my talk will be composed of several parts. So I will start with giving a little bit of more extended introduction, given that the field of research is relatively new. So I will talk a little bit like a hand-waving basing theoretical concept that concern two-dimensional magnetism. And then I would like to illustrate a little bit these different concepts, the different type of magnetizations that appear by doing a little bit of the review of the current state of the art. And then finally, in the third part, I will talk about our results of how we characterize this thin films of comparatively of chromium bromide and chromium iodine by photoluminescence in magnetic field. Two-dimensional layered materials that display different types of magnetization are known for a very long time. And there is a great number of different compounds that have been characterized already decades ago in their bulk form. However, the isolation of a very thin layers, in particular atomically thin layers, was not possible until recently, mostly because many of these compounds are not stable in ambient conditions in the limit of atomic thickness. So that required a little bit of technological progress. So one of the common ways of combating this problem is isolating the thin layers in controlled atmosphere, for instance, in argon, and then protecting these films by encapsulating them, for instance, in a wide bandgap material such as hexagonal boron nitride. And then indeed, so one of the first reports showed isolation of chromium iodine as a function of thickness. So you can create devices, heterostructures that have one layer, two layers, and three layers of material, and then you can study the magnetization through different methods. One of the common ones initially used to study is the Kerr rotation, when you measure the rotation of the linear polarization in the reflected light induced by the presence of magnetization. And then you find, for instance, that a monolayer and a trilayer film of chromium iodine behaves like a typical ferromagnet, so it shows a hysteric behavior of magnetization, while a two-layer film behaves completely differently. So it behaves in a way that individual layers show ferromagnetic order, but the layers are coupled to each other via antiferromagnetic interaction. So there is no net magnetization without external magnetic field, but then by applying external perturbation, magnetic field, for instance, you can flip the direction of the magnetization on one of the layers and observe non-zero net magnetization. So one could argue that the two-dimensional magnetic systems existed for a long time, for instance, in a form of magnetic quantum wells. However, probably it's difficult to argue that actually a monolayer atomic film of atoms that display magnetic moment is perhaps the best possible realistic realization of a two-dimensional magnet. So the question of emergence of a magnetization over large scale is related to the processes which could allow the orientation of magnetic moments in large scales. So such a type of interaction, which we call, for instance, ferromagnetism, is related to the breaking of the symmetry that is usually preserved by many other types of interactions in solid, and this is called time reversal symmetry. So this is a symmetry when you flip the orientation of the spin, you flip the orientation of the orbital momentum, and then you flip the orientation of the magnetic field, and most Hamiltonians preserve or are the same under such a transformation. However, ferromagnetism is one of the many body processes that breaks this symmetry, and one of the ways to do that is via so-called exchange interaction. So this is a type of interaction between two spins, two neighboring spins that you can write in the form of a vector product of two spins with a parameter that is called an exchange coupling constant. And depending on the site of this exchange coupling constant, you have two types of interactions. So if the exchange coupling constant is bigger than zero, then the parallel alignment of spin has lower energy, and then we call such a state a ferromagnetic state. Or if the exchange coupling constant is smaller than zero, then anti-parallel alignment of spins forms a ground state, and then we call it an antiferromagnetic state. And the question whether this kind of coupling between spin can extend over macroscopic scales is very closely related to the problem of thermal fluctuations that could rise low energy excitation that may in principle destroy such order. So from a theoretical perspective, the situation in two extreme cases, three-dimensional and one-dimensional, is very simple. In a three-dimensional arrangement of spins, the spectrum of the spin waves is continuous. There is no gap. So at any finite temperature, you can excite spin waves that leads to the destruction of the long magnetic order. In one dimension, it leads to the destruction of the magnetic order. So for a chain of spins, you can never have an arrangement of spins at finite temperature, only at a theoretical limit of 0 Kelvin. However, in a three-dimensional cases, the spin spectrum of the spin waves opens up a band gap. And this band gap determines a range of temperature in which you cannot excite spin waves, and then magnetic order may be preserved. And the situation of a two-dimensional alignment of spin is very different. And the problem of whether the magnetic order may exist is also linked to another parameter that is called spin dimensionality. So a spin dimensionality is a parameter which tells you how many of the spin components you need to give in order to fully describe your spin systems. So for a highly anisotropic kind of interaction, when the spins are only oriented in one direction, you have a case of spin dimensionality 1. When your spins are only aligned in the plane of your material, then your spin dimensionality is equal to 2, and these are so-called planar magnets. And if you allow the spins to be oriented into any direction, then you're talking about the isotropic exchange interaction, and the spin dimensionality is equal to 3. And then there is, as has already been discussed many times, a Mermin-Wagner theory that distinguishes these two cases of spin dimensionality 1 and spin dimensionality 3. So the spin dimensionality 3 is so-called described by so-called Heisenberg model, and just like in a three-dimensional spatial arrangement of spin, in this kind of model, it's a gapless. It creates a gapless spectrum of spin waves, so that the magnetic order may not exist in this configuration. However, if you have a strong anisotropy, which forces the magnetic interaction to occur only in one direction, then again, this opens up a gap in the spin spectrum, and similarly, magnetic order may be created. The case of the spin dimensionality 2 is much more complex, and one of the theorems that talks about this case is so-called Berezinski-Kosterlitz-Toules theorem. And it predicts a creation of state which is very peculiar. And this is a state that has no net magnetization. So the situation does not change with the temperature. However, it predicts a transition at a certain critical temperature where the susceptibility of the material goes to infinity. So that it doesn't have net magnetization, but it is extremely sensitive to external perturbation in the form of external magnetic field. And so such a state, they can be observed, for instance, in a very thin layered superconductors and Josephson junctions, for instance. So in terms of a thin films of two-dimensional materials, we would expect that if we see any magnetic ordering, that it must be in the case, then the type of magnetic interaction is of the Ising type. And then in order to find some simple classification, we can say that we can consider different arrangement of the spins with respect to the in-plane exchange interaction and interlayer exchange interaction. So in a simple version, you can say that you have 4 possible configurations when the in-plane interactions is either ferromagnetic or antiferromagnetic, or the interlayer exchange interactions is ferromagnetic or antiferromagnetic. And even though we have been studying these magnetic materials in the thin layer form for a very short time, we already know representatives of materials that display all these different types of arrangements. And on top of that, these materials are very different from the point of view of their electronic properties. So some of them are semiconductors, some of them are insulators, some of them are metallic. So you can say that each of these material, and especially its structures of a different thickness, can create completely different systems with a variety of different physical phenomena to be explored. And in order to take advantage of that, then we need to apply a variety of different methods. So I would like to give you a little bit of my view of what are actually the main directions currently to characterize these fields. So as I said at the very beginning, a common method is to use the optical methods that directly observe the magnetization, such as Kerr effect, Faraday effect, or magnetic circular dichroism. And then you can look how the magnetization involves in the layers of different thickness relatively easily. So another way to create a similar type of observation of the evolution of magnetization is by fabricating tunneling devices for materials which are semiconducting or insulating. And then when you measure the resistance as a function of magnetic field, you see similar jumps, and as you see in the optical methods. And also in that way, you can recreate this jumps by developing a simple models when you say that the resistance of the film depends on the magnetization in the layer. So if the tunneling electron has a spin up or spin down, it will have the device will have a different resistance in these two cases, and in such a simple models, they reproduce quite well such a magnetoresistance spectrum. So apart from just looking at the magnetization jumps in the tunneling spectra, you may also observe the appearance of narrow resonances, then show dispersive behavior when external magnetic fields are applied, and these are attributed to the processes when the tunneling of an electrons and holes is mediated via magnons. So these experiments are doable for insulating materials, but there also exists a class of materials which is metallic. And then you can create a heterostructures that you use metallic magnetic materials as electrodes. So this is an example when you have a tunneling device based on hexagonal boron nitride material. And then again, when you measure the resistance of such a heterostructure in external magnetic field, you see this kind of rapid jumps that display a kind of textbook spin valve behavior. And these jumps correspond to the situation when the coercive field of the two electrodes is slightly different. So you have a regime that you have a tunneling in either a case that the magnetization is parallel or anti-parallel in your magnetic electrodes. And then you can combine the methods of electronic transport and optics, and you can try to control magnetization by electrical methods. So this is, for instance, some data using a double-gated devices that you can independently apply electric field or induce doping of the material, and then you can observe how these effects change the magnetic state in the thin layer. So this is an example for a bilayer chromium iodine. As I mentioned, two layers are ferromagnetic, display ferromagnetic orders, and they are coupled antiferromagnetically to each other. And you can change this interlayer type of ferromagnetic coupling into antiferromagnetic coupling by applying external electric field, or by doping, you can shift the magnetic field at which the magnetization in one of the layers is flipped. So overall, there is a huge parameter space to be explored, and there is a variety of methods that can be used to study these materials. So now I would like to select just chromium iodine and chromium bromide as the two representatives of the same family of magnetic layered materials, and somehow comparatively discuss their properties in terms of photoluminescence response. So chromium trihalides, so these are materials that the chemical formula you can write as chromium X3, where the X is the halide atom, so it can either be chlorine or bromine or iodine. And the configuration of electrons on the valence band for chromium is so that it has a half-filled 3D shell, which is the origin of the emergence of the magnetization due to the half-filled D shell. And the halide atoms, the valence shells are made of S and P orbitals. So these are the orbital wave functions that will contribute to the creation of the electronic bands in this material. So in terms of the crystal structure, a monolayer of chromium iodine is made of 3 atomic planes. So the middle plane covers chromium atoms, and if you look from the top, these chromium atoms show a hexagonal lattice, and then there are 2 layers. It's encapsulated between 2 layers of halide atoms that also show they are a little bit shifted, but each of these layers is also hexagonal. And in terms of the bark crystals, it is a 3-layer structure, similarly to ABC stacked graphite, that constitutes a repeated motif that creates thicker structures. So predicting the band structures of these materials is very complicated, because the actual character of your band structure will depend on the type of the magnetic order that you assume exists in these materials. So these are the calculations for different scenarios, how the magnetic interactions occurs. And then you can see that they are not very, they do not agree well with experiment, because in some cases you can predict that this is a metallic state, while for instance, in transport experiments, you can see that it is an insulator. So these predictions without experimental support are not very reliable, but some basic observations still can be made. So these calculations predict that both the valence and conduction band of these materials are made predominantly of the free orbital of the chromium atom, with a little bit of a mixture of the p orbitals from the halide atoms. And because the 3D orbitals are very localized in real space, it leads to the creation of extremely narrow bands, which are obviously responsible from the many-body correlated effects in these materials. And the value of the band structure is predicted to be of around electron volt. So since we expect that the bands are made mostly of the orbitals of the chromium atom, it might be helpful to look at the photoluminescent spectra of chromium atom itself. And then you can look at how the emission looks like of chromium atom, for instance, as a dopant in well-known semiconductors such as gallium aluminum arsenide or zinc selenide. A slightly different chromium atom because it's 2+ and not a 3+ like in this case. But kind of ubiquitously, the optical response of chromium atoms appear in form of a very broad band in the near-infrared spectral region. And if you look at the photoluminescent spectra, for instance, from chromium iodine and chromium bromide, you indeed see that they are very similar to those of the chromium atom itself. And they are made of these very broad emission bands. And if you look at the evolution of these emission bands as a function of the layer thickness, then you can see that the energy of the emission is practically independent from the monolayer limit all the way to the bulk. The intensity is a little bit increasing, most likely because you're just putting more material, so you can create, the absorption is bigger, you create more electron hole pairs. And then if you look only not at the emission, but also on absorption, so this is a result of a photoluminescence excitation experiment when we tune continuously the energy of the laser and look at the emission intensity, and we observe that a similar band is also observed in absorption at the higher energy side. And for some samples, you can also see that there appears a very narrow line roughly in between of the emission and absorption band. And such a type of optical response is very, very characteristic of an emitters that follow so-called Franck-Condon principle. So initially, this Franck-Condon principle was developed for molecules. So if you have a molecule, you have a HOMO-LUMO levels of the molecule, so 2 electronic levels. By shining light on them, you can elevate an electron between these 2 electrons. And these levels for a molecule, they are coupled to vibrational mode. So that you not only have 2 electronic levels, but they are coupled to a ladder in a harmonic oscillator approximation of equidistant vibrational modes. And then what happens for a molecule when you shine light, you can elevate this electron to many different vibrational modes. At low temperature, you would see a relaxation to the ground vibrational state, and then you would observe emission to all of this vibrational mode coupled to the lower energy state. And all of these transitions, they usually merge and create these broad emission bands. while one of this transition that doesn't involve any creation or annihilation with vibrational mode is called zero Phonon Line, and it's usually characterized by much larger oscillator strength, so it is visible as a narrow resonance. So this kind of spectrum creates exactly this kind of response that we observe for chromium bromide or from chromium iodine. And the way that you can have this kind of Frank-Condon emitter in a solid is if you consider a Frankel exciton. So this is an exciton and electron hole pair that is localized so much that it occupies pretty much a single atomic cell in the crystal. So it has a molecular-like character. So the arguments why we would expect to have such kind of Frankel excitons in these crystals is that the band structure is made of d orbitals, so that the excitations are very localized in space. And we also see in the evolution of the spectra with thickness that the energy does not change, which would be understandable because if the exciton is localized in a single atomic cell, then it doesn't really feel if you add more layers on top of that. It is still sitting in one layer in one atomic cell. And actually, you can actually see more of these transitions with phonons, because in a crystal, phonons take role of the vibrational modes. As you subtract this broad emission bands, you can see that the zero Phonon line is followed by additional narrow resonances. And when you compare these resonances to the Raman spectrum of a chromium bromide, you can reproduce these lines by assuming the transitions either with emission of a single phonon or a multi-phonon processes, so that it creates this kind of complicated response, but which can be understood in terms of phonons in chromium bromide. So in this kind of system, when you increase the temperature, what you expect is that you are going to depopulate the zero Phonon line, because you will start populating the higher vibrational modes, and that's exactly what we see. We see the decrease of the zero Phonon line intensity, while initially the intensity of the phonon sideband is increasing. So that's again a behavior that is expected from a Frank-Condon emitter. And then below certain temperature, you probably activate more and more non-radiative processes as well, so that at higher temperature, the total intensity starts to decrease. And then you can look at the magneto-optical response. So you measure intensity of the emitted light in circular polarization. So this is an example of the data for a bulk chromium iodine and a bulk chromium bromide. And then you see that even though in the bulk limit, they are both expected to be ferromagnets, they have a similar crystal structure, similar electronic structure, the behavior is completely different. So chromium iodine displays a very, very large degree of circular polarization that you can flip by changing the orientation of magnetic field. And the chromium bromide displays a little bit of the polarization degree of the order maybe of 10%, but it is completely independent on the application of external magnetic field. So a simple way how you can think about that is that, well, unlike a Kerr rotation, you don't just probe magnetization by photoluminescence, but what is important here is actually how electron and holes are coupled to the magnetization. So you may consider different scenarios. So for instance, you can consider that electron and holes are coupled to the magnetic moment of the chromium atoms via the same type of coupling, for instance, ferromagnetic. Or you can have a situation that electron and hole are coupled to a magnetic moment of a chromium atom in the opposite fashion. So one is coupled ferromagnetically, the other is coupled antiferromagnetically. And that creates a different types of the optical selection rules. So for instance, in this case, you create a spin imbalance when you induce magnetization in your layer, so that you have more electrons and more holes with spin up configuration than spin down configuration, and then you observe a large degree of the circular polarization. While when you have the opposite type of couplings, for instance, you have more spin up electrons, but you have less spin down electrons. So both of these transitions are equally probable. So the efficiency of this emission is the same, and that would lead to a situation that that there is no polarization degree or very little polarization degree. The splitting here is different. So the main point of this, that even though structurally and from the point of view electronic structure, these materials are similar, there might still be significant differences between these materials because there are more parameters involved, such as coupling of the band carriers with the magnetic moment. And also by doing photoluminescence, you can also see correlated behavior, for instance, by observing such a hysteric evolution when you sweep magnetic field in both directions. And this is strongly related to the breaking of the time reversal symmetry. Because breaking of the symmetry means that if you flip the orientation of the magnetic field, you do not have to preserve the spin and orbital momentum. So you can have the same value of magnetic field and two different configurations of your spin or magnetic moments of electrons. And that's all I wanted to talk about today. So a little bit of take-home messages. So first of all of these crystals, magnetic, two-dimensional materials, they are extremely broad in terms of a combination of a magnetic phenomena and electronic properties, so that practically each material constitutes a completely different physical system, and also you can get different systems by fabricating structures, for instance, of different thickness. And then a great advantage of the two-dimensional character is that you can use the van der Waals technology to create heterostructures without worrying to having to adjust or match the lattice constant. So you can combine the properties of many different materials. You can create complicated stacks of different magnetic materials or magnetic materials and non-magnetic materials and devices. So the parameter space here to explore is almost infinite. And as you very well know, all of this magnetization, collective phenomena, they do have a lot of applications. For instance, in information storage. So in a longer perspective, if there are more technical developments, technological developments, so for instance, raising the critical temperature is obviously an issue to room temperature. But such atomically thin films, they could show a lot of perspective from the practical point of view as well. And even though that this is a relatively new field, new field of research, there are already several reviews that covers these topics. So if you are more interested about these different aspects I've been talking about, they are covered in these reviews. So thank you very much for your attention.